Here I will introduce you to the theory of Faraday's law, and we'll apply Faraday's law to many qualitative and quantitative examples in class. Jumping right into the statement of the law, we have that induced EMF is equal to the negative of the time rate of change in the external magnetic flux. That term right here will be computed through one loop of wire, and if there are multiple loops of wire in our particular case, we will multiply by capital N the number of loops of wire in that problem. The notations here, again, this is the script E for EMF, similar to what you've seen in the ideal battery back in circuits. It is not permittivity. It has units of voltage. It is not a force, but it will be the agent of force if you ask the electrons that are flowing in the wire. This EMF is going to serve to drive an induced current. And you'll see importantly in class that this induced EMF is a manifestation of a non-conservative electric field that will violate some of the ideas that we have, such as the Kirchhoff voltage law when traveling in closed loops. This minus sign is a statement of Lenz's law. We'll talk about that later, and this will form the qualitative basis for many, many conceptual types of questions. We'll remind you, when finding the magnetic flux in Tesla meters squared or Webers, we're going to look at our surface A, consider the magnetic field everywhere across that surface, take the dot product of the field with the local infinitesimal area vector dA. That external field dotted with dA must be added up in every location across that area. Ultimately, the simplest case where that external magnetic field is uniform across your area, the simplest case will just give you the dot product of the external field and the area vector for the entire surface A. In computing Faraday's law, you're going to have to take a time derivative of that external flux. Well, a time derivative is independent of this integral over the surface A. So what you'll need to do is think about the possibility that three of the elements going into your flux could be changing in any given problem. So remember, we use the word constant to describe things that do not change in time, uniform to describe things that do not change in space. In order to change magnetic flux in time, you could change the B field magnitude with time. You could change the area that you're integrating over with time, or you could change the angle, the orientation between the B field and the area vector. If all three of these things are constant in time, your time derivative of the flux will be zero. There will be no induced EMF, and there will be no induced current in any sort of loops of wire that are exposed to that magnetic flux. Lenz's law, I said, was the minus sign in Faraday's law. It tells you that the induced current must oppose the change in the magnetic flux. More specifically, in words, the direction of that induced current produces induced magnetic flux, which will oppose the time change in the external flux, phi sub B, magnetic flux, external. So we have two different fluxes that you're going to need to keep track of. There will be the pre-existing external magnetic flux, through your loops. And then there will be whatever response Lenz's law determines by inducing an EMF, which produces a current in the loop, which produces magnetic field, and generates an opposing magnetic flux to that change in the external flux. We'll see you in class for many applications of both Lenz's law qualitatively and Faraday's law quantitatively. Don't miss it.